The most important thing for this talk that you need to know is I have a bag full of chocolate, and there will be lots of options for you to earn one of these wonderful Wawel chocolates during the talk. So do heckle, do kind of complain, and we'll see how we can distribute chocolate most fairly in this community. So there will be lots and lots of links and lots of books and references I'm going to mention. You can download the slides from this URL later, so you don't have to go and kind of type the URLs directly. And what I was going to kind of talk about today is how we deal with complexity. That's kind of always a topic for software stuff because we pride ourselves on kind of managing complexity very effectively. And the other thing that kind of tends to happen with software projects is kind of software projects are a bit like developers. The older I get, the more complexity I get. And there's nothing that can stop that. And we need to kind of figure out how do we manage that in a good way. And one of the kind of things that starts happening is as software projects grow, we get this kind of thing that the projects grow and grow and grow. And there was this famous, Jamie Zawinski formulated this law of software envelopment that basically says that any program is going to grow until it can read email. And those programs that can't read email will kind of die and be replaced with something that can read email. And that's kind of a joke rule. Fred Brooks said something similar, I think, in the vein of the destiny of any successful software product is to become an operating system. And it's going to grow until it either becomes an operating system or it's going to die before that and collapse under its own complexity. And one of the things that really got me to be a bit more philosophical about this is last couple of years I've been building my own product, and it started as something that kind of is really scratching my own itch. I was doing marketing materials for a different product I built and had to create lots of kind of online videos and realized how I really hate hearing the sound of my own voice and how I'm not a kind of voiceover artist and it takes me 3 hours to create a 5-minute video, and that's a waste of my time. And I'm not an editing professional, so it takes me a lot of time to do these things, and I wanted to kind of automate that. I'm a developer, I thought I can automate this. And I kind of built this thing that you can kind of look at the thing on the left, it's Markdown, and it kind of says, oh, play this part of this MP4 file, paint some words on top of it, use kind of text-to-speech engines to generate something, and it kind of creates a video out of it. And after I built this to scratch my own itch, I launched it as a product, and I'm kind of really confused how one thing led to another, but last year there were almost 10 million active users of it. And I'm still the only person building it. I'm the pre-sales guy, the post-sales guy, support person, developer, coffee lady, and everything in the company. And in order to manage that, I really had to kind of get the complexity under control. And I got a bit philosophical about this, and kind of some of the conclusions that helped me do this I want to communicate to you. So maybe you can take some of these things and apply to kind of controlling your own complexity in the company. So first things first, we are kind of going to look at what leading industry experts say about this, and this is from the Product Management Institute, the famous oracle of knowledge for everything to do, that's good. And they have this document called Strategies for Planning Complex Systems Development. So I was thinking like, I need to look at what the Product Management Institute claims are good strategies. And this is very illustrative of kind of what people write when they're talking about complexity. But all it gets like is some meta-level bullshit. Because their key strategies for planning complex systems development are kind of, make smaller things and then integrate. Thank you. Yeah. That's as much as the Product Management Institute can help us do with complex stuff. It's like, most of this is really, really meta level things. It's like Zen, to resolve something, first look within, or some bullshit like that. And it's not actionable. And I wanted to kind of look at what are some actionable things we can do. So that's kind of probably where I would like to take this talk, and maybe this is kind of going to be partially a conversation as well. So in order to do this, I want to involve you in figuring these things out together. And the first thing is kind of who in the room studied anything related to physics? So we have like a couple of people in the room. So let's see how much you remember. So first law of thermodynamics. Who can tell me what that is without looking at their phone? And earn a chocolate. This is your first chance to earn a chocolate. Yes, you can do it in Polish. So wait.
I was right.
Do it in Polish again.
Jeżeli na ciało nie działa żadna siła, bo działające siły równoważą się, to ciało znajduje się w spoczynku bądź porusza się ruchem jednostajnym, prostoliniowym.
Woo! Okay, so
Studied education.
here's your chocolate. I have no idea whether what you said was correct or not, but let's assume it was. So the first law of thermodynamics, in English, I'm going to translate what you just said, is basically you cannot create energy out of nothing. Energy is conserved, and a very important aspect and kind of constraint of the law that it's in a closed system. You cannot add or kind of destroy energy. It gets conserved. You can transform it from one shape into another. And this thing as a conservation law, it's one of the most popular conservation laws, inspired a bunch of other laws. One of my favorite conservation laws is the law of conservation of ninjutsu. Now, without looking at your phone, does anybody know what the law of conservation of ninjutsu is to earn another chocolate? Wait.
Is it the one that says that one ninja is more dangerous than 1 million ninjas? That the power of combined ninjas is proportionate to the number of ninjas?
Good. Yes. So we have the law of conservation of ninjutsu. For another chocolate is that the basically, if you have two ninjas. Oh, we have a microphone, excellent. Basically, the law of conservation of ninjutsu says you cannot create or destroy ninjutsu in a movie scene. And ninjutsu is going to be constant. So if you have two people fighting, they're going to be fighting for 10 minutes and they're really, really strong. If you have one guy fighting 20 people, he's just going to do and kill all of them. Because their combined ninjutsu is the same. And kind of that again inspires lots of similar laws. In software, there is a famous law defined by Larry Tesler, who is a UX expert, and says there is a law of conservation of complexity. We cannot create or destroy complexity. Every application has kind of some complexity inherent in it. We can just move it around. And whenever software people talk about, oh, we're doing this to reduce complexity, that's kind of against Tesla's law. We cannot reduce complexity, we can shift it around. What Larry Tesler is talking about is you can make your application more complex, and then the user's workflow becomes simpler. Or you can keep the user's workflow more complex, your application is simpler, but kind of any of that stuff around, but some complexity is there, and it's just up to us to figure out how we move it around. And kind of effectively, the main job we have as software developers, product people, engineers, testers, whatever, is when there's something like this, kind of to figure out whether this thing is better than this, or some combination of that. How do we encapsulate complexity? How do we manage it? How do we kind of push it around? About 15 years ago, I was working with this company where we were trying to build a system for affiliate marketing. We were kind of looking at this from a perspective. Affiliate marketing is where you have a growth engine that independent websites bring people to your website and you give them a percentage of the sale. So you create a link, they bring people there, and we had this kind of idea discussing what we need to do and how to model it. And one way of modeling it is we had our users. The users had like first name, last name, payment card, and something like that. And then we had affiliates. Because this was United States, affiliates were being paid by check. This is kind of still amazing for me that anybody's getting paid by a piece of paper. But hey, so the affiliate had a company name. It was a company and a check delivery address. The users had kind of personal stuff. They were private people. It was one way of kind of modeling that. And another way of modeling that was to look at, well, you know, we have an account. The account has a name, address, and some billing method. Whether the billing method is a credit card or a check being paid out, I don't know. It doesn't matter. And then we have, like, you know, a commission on that account. So we were arguing for like 3 days about these two ways. One guy was talking about how one way is better than the other and talking about this. And whenever kind of there's multiple options like this, the question is like, which one is better? And which one is right at the end of the day? So there was a really nice rule I remember from Box and Draper. They were market research people, and they were talking about how pretty much any model you have is wrong, because models are abstractions of reality. A model is not supposed to capture reality as the reality is, because then it's pointless. Yes, I as a person involved in this have a name, last name, and address, but I also have a blood group, shoe size, children, interests and things like that. Should that be in the database or not? Really, that's kind of a question of what we're trying to abstract. And modeling complexity is mostly about figuring out what we abstract away and what we keep. Again, we can only shift it around. So Box and Draper said that kind of all models are wrong, but some are useful. And really, you know, then the question is not which one is right, which one is more useful. So we have these two options. One is kind of affiliates users, the other is account name and affiliated commission. So I'm going to get you to vote now. And kind of you can vote on your phone either by entering this URL or kind of scanning this QR code. When everybody does that, I'm going to switch to the kind of voting screen so we can figure out what you think about this. Okay, so kind of okay. 4159, good. So let's talk about this a bit. So the people kind of saying that affiliates users is more useful than account commission. What's your opinion about that? Why do you think that's good? Can we get some light here a bit more, because I can't see people and I can't throw chocolate at them. Yeah. I mean, somebody who voted for kind of affiliates users, why? Is it just the first option and then, okay?
I can be the one. So that's just the intuition. I'm not an expert in the field, but it feels like there's a direct connection between the sales model and the user. So it feels like more natural.
Yeah, okay. So, you know, in domain-driven design, Eric Evans talks a lot about how we need to use the same language as the business. We need to kind of map it to the ubiquitous language of the business. People are talking about users and affiliates from the business. That makes sense. So other people kind of looking at account and commission, kind of somebody for a chocolate, who would like to explain the reason behind that? Oh, we have two options up there. Good. Yeah, I can. Here's a chocolate as well then.
Great. I got a chocolate, so now I can be silent. So yeah, I thought about potential use cases where somebody is sharing the account, the way we have two actors under one also creating multiple accounts. I don't know, somebody is, for example, using 2 different social media profiles of theirs, and they want to kind of like invoice it separately or something. So yeah, I thought that it may serve some future scenarios.
Okay, so we might have some, and there was another kind of hand going up there. So I'm gonna kind of, can you pass the chocolate up, please?
In my opinion, in both cases, you will achieve the same result.
Aha, so it doesn't
But
matter.
the maintenance and
Maintenance.
some other things may be more complicated.
With which one?
In my opinion, the second one.
Second one is more complicated for maintenance.
For me.
Okay, good, good. So here's what happened kind of with this thing. We kind of decided that we were going to do option number 2. That was kind of account and, and balance and billing method. And then a month later, the client said, oh, you know, now we want to change this stuff. We would like to get users to be able to be affiliates for other users, not just companies. And the sales guy looked at the kind of this, and he came and told us, like, how long does it take you to change this? And we said, well, kind of, it's already supported, really. And he came back to the client and said, well, you know, 3 months of work, it's going to cost you this much. And then after 3 months, the client came back and said, well, now we want to do maybe like a multi-level affiliate scheme where affiliates can be affiliates for other people. How long does it take to change this? And the sales guy came to us and said, look, you know, give me an estimate for this. And he said, well, it's already supported. And he said, okay, 3 months and, you know, this amount of money. And in terms of which model is more useful, like purely from the perspective of extracting money from the customers for no work at all, the second model was more useful. From the maintenance perspective also, the second model turned out to be more useful, but kind of just let's throw away this whole, you know, nasty behavior of charging for something that, you know, involved no work at all. If you just look at the speed of adopting things, the speed becomes kind of really interesting here because as kind of this lady over there mentioned, if you look at some future scenarios, the speed of developing these future scenarios is much easier with one option or the other. And Eric Evans actually in domain-driven design talks about this. He says that kind of a model is more useful if it can change symmetrically with the business. If a small change in business is a small change in the system. If a small change in the business is a big change in the system, then the model is not that useful. Now, of course, that requires us to predict the future, which is not that easy. And you had some changes in mind. We had some other changes in mind. Those changes might or might never come. And building a system to deal with changes in the future that never come is also a wonderful way to waste everybody's time. So there is a difference really between kind of building all this change and enabling system to handle that change. And there's another kind of problem with this. So for another kind of piece of chocolate, who remembers the basic speed formula from physics? How do we calculate speed? Phil.
Distance divided by time.
Distance divided by time. Here's a chocolate, good man. That's good. So we have kind of in physics, speed is distance divided by time. In software, it still is, but with physics, you can kind of look at this formula and you can think that if I change the distance or if I change the time, the speed changes, and you know that's fine. We can control it that way. Bruce Tonazzini, who was a UX designer at Microsoft, basically figured out that in software, you cannot actually change one of these things. And he says kind of in software, really, he said this kind of law of commuting, the time of a commute is fixed. The only thing that really varies is kind of the distance. And what he meant by that is that people have half an hour to do something. You give them a software system, they still have half an hour to do it, but they can get further with that. And that changes the context. Our products actually change the context. So when we're talking about what are the potential changes that can happen, we can't predict them up front because the context changes when we give people something. When we give people a software system that has users and affiliates, they start thinking about, oh, now I can have sub-affiliates. They were not thinking about that before. And kind of, TOG has this kind of paradox applied to Tesla's law that basically says once you give users something, they start doing more complicated things. And what he's saying is basically Tesla's law is wrong. Tesla talks about how the complexity is conserved. TOG says, well, complexity is not conserved, it actually increases as a result of our work. You cannot reduce it, but it does increase on its own. A nice example of that is VisiCalc. VisiCalc was the kind of key killer app for the Apple Macintosh 2 in 1979. VisiCalc is the first time somebody probably properly automated a spreadsheet. And at this point, Dan Bricklin, who kind of programmed the first VisiCalc, he thought he's going to do this for accounting kind of calculations and things like that. And then he said he started getting emails from people saying, oh, you know, we started using VisiCalc and now I can finish the whole day of work in 1 hour. And then I just spent the rest of the day slacking off and didn't do anything else, but people still think I'm a wizard. Thank you very much. And then he said, you know, companies figured that out and started giving people more complex things to do. So all of a sudden you had to fill up the other kind of 7 hours working with your time. And people started using VisiCalc in unpredictable ways. Like they started using the spreadsheets to plan hospital beds and all of the stuff that nobody knows about. And now you have, like there's a Japanese guy who like draws Japanese paintings in Excel with numbers and things like that. So kind of crazy stuff that happens because we give people something to do. And that's another kind of really important thing to consider. So kind of really the first rule for dealing with complexity here is because complexity is going to increase as a result of our work, we need to kind of figure out what are the potential vectors of change. We might not be able to predict everything, but it's kind of reasonable to look at something and to say, well, you know, we have a payment method, we have at least 2 payment methods, we have checks and we have cards. Is there going to be a third payment method in the future? Possibly. You know, so we need to kind of start figuring that thing out. And I think that's one of the things that we as a community lost in the last 20 years. When I started making money from software, one of the kind of most influential books I read about this was Jim Coplian's book on multi-paradigm design in C++. It even sounds very kind of, you know, pompous and engineering and things like that. You can see it's a serious book. But Jim wrote his, I think it was his PhD on analysis of variance. And he came up with this design technique called commonality variability analysis. You know, 25 years ago, analysis was kind of a big thing. And we've thrown it away completely. But the core idea that Jim is talking about in this book, you don't need to know C++ to kind of understand the core idea, is kind of figure out what are the common things, what are kind of the things that are likely to change in the future, and where are the possible dimensions of change, where are the possible vectors of change, and then to apply kind of the design that matches that. And that's kind of the reason why we selected this one design over the other, because we figured there's some commonality here. There's a commonality where they have an address, they have a payment method, there's a variability within that commonality in this case. And if you are using C++, then Jim's book says, oh, if you have a commonality in names but variability in behavior, use this. Or if you have a commonality in behavior, variability in kind of process, use this other thing. That's really too complicated, and hopefully you're not using C++ anymore. But what I'm trying to say is that there are kind of these analysis techniques that we've thrown away, and we should kind of really, you know, not reinvent the wheel. And we can predict how things are going to change and model for that. And of course, kind of the problem is when you start changing things, then, you know, there's lots of pressure to kind of move things around. And there's kind of another opportunity for a chocolate now that's kind of from physics. Does anybody remember Boyle's law? Looks like I'm going to eat this chocolate myself. Okay, so nobody gets a chocolate this time. Boyle's law basically is one of the basic rules of physics. It says that an ideal gas, whatever an ideal gas means, it's not a fart, it's something kind of that smells nicer. An ideal gas applies pressure inverse to the volume, which kind of translated in plain English means a gas is going to expand to fill a room. The larger the room, the more the gas expands. And translated to software, there's an interesting way of translating this to work, defined by Cyril Northcote Parkinson, called Parkinson's law. Parkinson's law is basically that work expands to fill available time. If you have a week to do something, you're going to do something in a week. If you have 3 months to do something, you're going to figure out how to do it in 3 months. Stuff is going to come up. And Parkinson actually kind of concluded this from a research he's done with bureaucratic organizations in 1950s. His research was published in The Economist in 1956. And one of the most interesting conclusions from that paper, it's a fascinating paper, is that bureaucracy in organizations grows 5.6% per year, regardless of what you do. It really doesn't matter what you do or what you don't do, bureaucracy grows 5.6% per year. I don't know exactly how he came up with this precise number, but it sounds correct from my experience. And the problem with this is, again, as we do things that are supposed to stay alive for 5 years, 10 years, shit just grows around it. People will find more work to do because of kind of these other things. And then we have all this kind of pressure to change stuff because of the bureaucracy. And people start hating bureaucracy. As a developer, I hate bureaucracy very much. We try to kind of optimize it away. We try to cut through it. Mark Schwartz wrote this fantastic book called The Art of Business Value, where he said that kind of hating bureaucracy is pointless. We really need to figure out how to work with it. And bureaucracy has its reasons. And he said kind of hating bureaucracy is like hating the law of entropy. So kind of, you can do that as much as you want. It doesn't really change anything. We need to figure out how to deal with kind of bureaucratic changes. So kind of that brings me back to another option for a chocolate when we look at entropy. Does anybody remember the kind of second law of thermodynamics? Oh, we have kind of somebody over there. Good. Thank you.
So I hope I will have this right. So the second law of thermodynamics is that the entropy in the system cannot decrease.
Yes, the entropy in the system cannot spontaneously decrease. That's good. Thank you very much. Woohoo! So the second law of thermodynamics says that basically a system that's left to spontaneous evolution, that's very important. A system left to spontaneous evolution does not decrease in entropy. The entropy increases. And kind of that's really important from kind of lots of different perspectives. Entropy is one of the core concepts of IT and software communication. Shannon's fundamental paper on information technology, on information exchange, that kind of why our industry is now called IT, kind of that was the first point where information was used as a thing, was talking about entropy. And entropy in communication lines. It was done, I think, in 1950s or something like that. And there was lots of stuff around how do we call it, what do we call it, and what do we do then. John von Neumann, who invented everything that needs to be invented around computers, talked to Shannon at this point. And John von Neumann suggested that Shannon uses the name entropy in communication. And when Shannon asked why, John von Neumann basically says that nobody knows what entropy really is. So whenever you have an argument, you can win because nobody knows what it is. So entropy always increases, nobody knows what it is. And we can always win arguments with that. If you want to kind of read more about this, the book to look at is called The Dream Machine by Waldrop Mitchell. It's wonderful. It talks about the origins of computing. I strongly recommend kind of people read that. Anyway, going back to the topic, we have entropy that's always increasing, and nobody knows what the entropy is. And there's kind of lots of other stuff around entropy that people talk about. Fred Brooks, in the Mythical Man Month, said that basically program maintenance, we talked about maintenance and making maintenance easy. Program maintenance is always increasing entropy. That's even more pessimistic than the physics one. The physics one says you cannot decrease entropy, but maybe it's going to stay the same. Fred Brooks says, no, it's not going to stay the same. Kind of entropy increases. And he says basically something very, very pessimistic immediately after this. He says kind of even the best people you have on the team, put the best team you have on it, all they can do is just delay the inevitable, which is kind of this thing collapsing under its own weight. Now, we can delay this thing for 50 years. We can delay it for long enough time, you know, to be useful, but we can only delay it. It's going into an unfixable mess. And that's really, really pessimistic. I hope we don't kind of end up just delaying the inevitable. But there is something here that really we need to consider. It's kind of, as we add more stuff to the system, it just increases entropy, it increases kind of cost, it increases all these other things. And the question is, are we really adding the things that make sense to add? There's a wonderful book that came out recently called Trustworthy Online Experiments by Ron Kohavi. Ron was in charge of experimentation at Microsoft, and he's some really interesting numbers from companies like Slack, Microsoft, Netflix, Google. So he talks about kind of the stuff they measured at Microsoft. One third of the things they measured actually delivered the business value that was supposed to happen. About 2/3 they measured did not deliver the business value that was supposed to happen as a result of that. They say that kind of for stuff that's well optimized, like he says Slack is reasonably well optimized, only about 20% of new ideas create any business value. 80% of what people do just increases entropy. He quotes Mark Moran from Do It Wrong Quickly, where he has data from early days of Netflix, where they considered 9 out of 10 things they did as wrong. Just increasing entropy. Now the question is, do we keep that shit in our system or not? How do we know which parts are working, which parts are not, and why do we even kind of do these things? So kind of Edgar Dijkstra basically said that one of the key things that a computing scientist, this is written in the 70s, so everybody was a computing scientist. Back then, I guess we would all wear lab coats and look really serious at the conference. He says basically the main challenge is not to confuse kind of the real complexity with stuff that we're inventing for no reason at all. And when you have a well-optimized domain like Ron is talking about, if 8 out of 10 things are wrong, then that's complexity we're introducing. That's not really the complexity that exists. And we don't need to kind of add that stuff. So kind of Fred Brooks again talks about this in his book, and he says that kind of there's 2 types of complexity we need to consider. One is what he calls essential complexity. That's complexity that's based, like the nature of this thing is complex, and therefore it's there. That's the complexity that Tesla talks about. That's the complexity that gets conserved. That's something we can simplify on one end and move on another. But then he says there's kind of this accidental complexity. And lots of people talk about accidental complexity without understanding what Fred Brooks talks about. Fred Brooks talks about this thing as kind of difficulties that are because of today's means of production. That means that everybody's doing microservices. You decided to do microservices. You have introduced some complexity because of that. Then there's complexity in monitoring, complexity in kind of replaying messages, complexity in lost messages and things like that. If you did a monolith, then you would not have lost messages. It's all in the process, but then there's other types of complexity and things like that. And he says kind of, we need to figure out, the key thing to figure out is the difference between these two. Because kind of the first one we can only kind of shuffle around, but the second one we've produced. That's kind of that's Togg's kind of paradox. We've produced that and we don't have to produce it. It's up to us not to produce it. So kind of rule number 2 really that I figured for myself is to actively fight accidental complexity and to realize when I'm introducing some complexity that doesn't need to be there, and to fight against my needs to kind of just fill up my time. If I have 2 weeks to do something, I'm going to fill it up with less complexity than if I have 1 month to do stuff. And kind of this is where, cutting stuff into shorter cycles and things like that can help because you have less time to invent your own bullshit. So the other kind of thing that's really interesting is why this thing happens. And there was a conference in 2002, early days of XP, where they invited lots of people from other domains. It was not just software people attending. And Enrico Zaninotto was an Italian economist who attended the XP conference in 2002. And they tried to kind of figure out what can the Agile community, not even Agile wasn't a name back then, what can the XP community learn from other practices? And Enrico basically talked about how in economy and rules that are people putting in around bureaucracy and things like that, the main driver of complexity is irreversibility. If you cannot reverse a decision, then people put in lots of complexity around that. And there was lots of discussions around how, well, yeah, that's kind of the same for software, really. Because if we can make reversible decisions, if we can make it flexible so we don't have to commit to one thing or another, then we don't have to introduce that much complexity. And this is where kind of Enrico talked about how lots of stuff that people were doing around iterative development back then, such as test-driven development to protect changes and shorter iterations and collaboration and things like that, they're preventing these bad irreversible decisions. Martin Fowler, kind of as a result of that, wrote this paper where he said the key role of an architect is to remove architecture, not to add architecture, but to remove architecture, where basically find ways to eliminate irreversibility. Simplify stuff by making things less irreversible. And this is where a lot of the, again, lean stuff and just in time and things like that comes in, where we don't have to kind of commit to stuff too soon. One of the best ways of doing that in software, if you want to look at this technically, I said I don't want to make this talk too zen and just like do small components and integrate them, is hexagonal architecture by Alistair Coburn, or kind of ports and adapters architecture. That's basically a way of creating an architecture, again, that was popular a long time ago and lost now, where we can design a system by isolating kind of the business logic from all the technical stuff, by isolating the true essential complexity from accidental complexity, because we know that accidental complexity is going to change. It's constrained by today's means of production. Today, microservices are popular. 5 years from now, something else is going to be popular, but the business rules are going to stay the same, or kind of they will evolve differently. And ports and adapters is a wonderful architecture that allows us to kind of switch different things and combine different things and reduce irreversibility. So I think this is kind of one of the main design tricks I've been using on my software to save a ton of time, and that's kind of saved me for more times I can remember. If you want to look at more details into this, Steve Freeman and Nat Price talk about this as kind of ports and adapters in their book on growing object-oriented software. It's, I said, that's one of the best ways of isolating two different types of complexity I figured out. So kind of now we have another option for a chocolate. Again, going back to conservation rules. Does anybody remember the law of the conservation of mass? Okay, I'm good. Oh, we have a chocolate here. Good.
La energía ni se crea ni se destruye, solo se transforma. The energy doesn't create or destroy, it's transformed.
That's the energy, but this is mass.
Sorry.
But you get the chocolate
I don't,
as well.
I don't need
Gracias
sweets.
for you. That's, so we have like similar to energy, like in a closed system, where in case of physics the temperature doesn't change. The mass kind of cannot be kind of changed. It cannot be shuffled around. And then there's a bunch of paradoxes to this, and part of this is kind of, they talk about in the law of conservation of mass that elements can change shape, they can still have the same mass. And one of the things that kind of is often used as a joke paradox to that is Costa's garbage mass law, which says kind of, how do we have 4 bags of groceries? You go and buy 4 bags of stuff in a shop, and then those 4 bags of stuff turn into 6 bags of garbage to throw out. And that suggests like we're creating mass. And garbage that we produce through kind of, and how we manage garbage in our software projects is really interesting. What do we throw out? What do we keep? And kind of going back to kind of, this is garbage. I'm going to kind of give out some chocolates now. Most of people now don't manage memory themselves. We use kind of memory managers and garbage collectors and things like that. How many garbage collector mechanisms can you name? Who knows kind of popular garbage collection mechanisms? Shout out and I'll give you a chocolate for any one of them. Mark and sweep, okay. So mark and sweep is a garbage collection where you stop everything, you go around, you kind of mark what's going on, and then you have another one that kind of removes stuff that's not used. Anything else? Okay. No, but that's okay. So there's a couple of others that people have invented over time. There's kind of generational, that's kind of speeding things up. There's kind of zero garbage collection that was introduced in Java relatively recently to avoid kind of the stopping process and things like that. There's another kind of really interesting one that's called the null garbage collector. Can anybody kind of think about what the null garbage collector does? Garbage collector that does not collect garbage. So it's a perfectly useless garbage collector, does nothing, but null garbage collector is an option in kind of all the dynamic systems today we have. And very often people don't use it, but sometimes, that's exactly the right thing we need to use. There was a famous kind of discussion on was it the C++ design list or something like that? I've pulled out the link for this from. So that's kind of documented. It was in 2005, and Kent Mitchell talked about, he was at Rational Corporation. They were working with this unnamed missile kind of software development company. I guess there's not a lot of missile software development companies in the world. And he said they were trying to chase some bugs in the software, and he applied lots of different tools to do static analysis, and he figured out that they have memory leaks in their missile control systems. It was like, memory leaks, that's not good. And then they came up with lots of proposals how to fix that, and he went with a proposal to the chief architect and said, we need to fix these memory leaks. And the guy said, no. I said, why? Like, memory leaks, dangerous, missiles, He said, no, that's fine. I said, but memory leaks, man, it's He says, no, look, we know that it leaks. Of course it leaks. That was the response. He says, it leaks basically at this rate, and we put twice the amount of memory in for kind of how long the rocket will fly to shoot at the Soviet Union. So the garbage collects itself. It never needs to kind of stay there for longer. So a lot of this, what I'm trying to say is that there are cases where it's perfectly fine not to do this kind of complexity, not to jump in and solve these problems that don't need to be solved in the first place. We need to figure out how this thing works and why it works like that, and understand that. So kind of Peter Naur had this wonderful paper, I strongly recommend everybody read, called Programming as Theory Building. That's one of these things, again, we've lost. And he talks about how basically any software program is a theory about how the world works. We model it, we explain it to ourselves, we automate it in some way. Our theory might be right or wrong. But kind of building up this programmer's knowledge about how the world works as we're programming is critically important. And likewise, it's critically important to communicate this to the next person. If people know that this thing is supposed to work only for 20 minutes, then you don't need garbage collection there. You don't need to invent all this accidental complexity. So kind of the philosophical principle behind that is called Chesterton's fence. Chesterton is a British philosopher who kind of came up with this idea that you go across a road and there's a fence on the road. And of course, that's dangerous. People can hit that with cars and whatnot. And your instinct is to remove the fence. It's just kind of, instead of just removing the fence, first seek to understand why the fence is there. And then if you understand why the fence is there and you still think it's good to remove, go and remove it. So we need to really figure out the why. That's kind of one of the things that is important. And building up this theory and teaching the theory of the system to other people is important. Now, there's a million ways of doing this. There's kind of architectural design documents, there's logs, and Jim talked about kind of visualizing the narrative. I pressed him on this morning. That's kind of the narrative of how things came to be. We need to keep that in one way or another to kind of maintain this because of the next thing. So Richard Cook talks about in How Complex Systems Fail that basically any change we do introduces new forms of failure. We have a system, we fix it, that introduces new forms of failure. We remove this fence, all of a sudden something else happens. And without really understanding that, we need to kind of figure out why and how this is going to be kind of managed. And there was another kind of case study of this that's really wonderful. That's the K-15 submarine. K-15 submarines were introduced in 1913 at the end of the First World War. They look really, really strange. You can see kind of the submarine shouldn't necessarily look like this. It's not kind of how most submarines look. The K class of submarines became known as the calamity class. 18 were built in total, 6 sank due to accidents on board. Like they were not sunk by the Germans. Lots of people died in them. It's really, really horrible. And there's a couple of things that they did the first time with the K class. K class was the first time where steam was introduced as a way of propelling submarines. And they didn't really know how this is going to work on a submarine. And the K class was tested to 20 meters depth, where it was longer than 20 meters. So kind of, if it started diving like this, the head would kind of go into unsafe depth, where the kind of bottom would still be at the top. And it was kind of unstable because of all the boilers and stuff like that. So the boilers started kind of creating new effects. That was a change people didn't predict, because what started happening is the boilers were here, or in the front, and as the boilers were working, the steam was pushing that part down faster than the other parts of the submarine. So the submarine was diving like this, and it couldn't hide properly. And then they started introducing more ballast there, so it looked like crazy like this. But then water started going in through there because of the ventilation shafts, and actually the water started going into the boilers that were boiling water for the kind of for the steam, and the water from the sea started shutting down the steam boilers, so the submarines would start sinking. It's kind of totally insane. And this was the result of an innovative technology experiment in production. And kind of effectively, it's one of those things where things fail in unpredictable ways. And we have this stuff today that we are introducing stuff like that all the time. Because of the internet, because of kind of unpredictable stuff we're doing, because of the new things we're doing. Jesse Robbins famously started this kind of game day at Amazon, where they realized that they're not doing things that anybody else has done before. They're creating these microservices out of containers that talk to each other, and stuff fails in magical, unpredictable ways. And the game day thing was designed to kind of inject failure there. This was kind of the first time I've read about people intentionally breaking systems to figure out what's going to happen, to inject faults to figure out what they were going to do, because he says complex systems tend to fail in unpredictable ways, but failure is inevitable. It's one of these kind of things we cannot avoid. So he says the best we can hope is to get these horribly unreliable components and to build something resilient and reliable on top of it. We can, the stuff we're doing today, if you look at like 99% of the businesses have some open source component that was developed by some poor guy in Finland who kind of, spends most of the winter drinking vodka. And you don't know about that. You don't know when he's going to get drunk and do something that's unpredictable in the software. We talk about unreliable, components talk through unreliable networks. Everything is online. Everything is connected to everything else. It's just a ton of stuff that can fail. And they were talking about how do they create a reliable software out of that. They came up with 4 principles. And the kind of key thing was basically to try not to make it perfect, but to make it resilient, because that's what the best they can do. The 4 cornerstones of resilience they talked about, where we need to know what we do, is first of all, kind of anticipate what's going to happen and monitor, because you have really no idea whether what you anticipated is the right thing to do, but you at least get something to monitor. And then kind of, once things start happening, figure out how we're going to respond. And that's what they were doing, injecting faults to figure out how they're going to respond to stuff. And then, cycle back and iterate and know what we're doing as learning. And I thought this is kind of really interesting as a principle generally for what we need to do to manage complexity and build resilient stuff. But the last part is the one that kind of finally, is interesting, because these things evolve through time. And we need to figure out how they evolve because of Togg's law, because of entropy, because of this stuff evolves outside of our kind of control. So we need to learn and respond to what happened. And one of the best cases for that is kind of the Ducati case study from 2003. Ducati is a motorcycle manufacturer. They wanted to compete in the MotoGP races in 2003. And they've never built that type of a bike before. So they knew that they were doing something for the first time. They didn't know what's going to happen. They knew that they're going to change their existing bikes to match kind of the racing constraints. And they did what Jesse talked about. So they built lots, they anticipated what could break, what could change. They built lots of sensors. They put 28 sensors in a bike. After every race, they would download all the data. Everybody would sit down, they would analyze, they would try to kind of figure out what went wrong, what went right. They would kind of tune the bike a bit, introduce new components. And something really strange started happening in the middle of the season. They started winning. Their bike was kind of the worst at the start of the season. In the middle of the season, they started winning. And by the end of the season, they finished second overall. Nobody expected that. They didn't expect it. Everybody was really kind of confused by this. And then they did what kind of companies usually do. For the 2004 season, they said, we take all the knowledge we had in 2003, we design a perfect bike. They changed 60% of the components between the seasons. They stopped measuring, they stopped monitoring anything, and they finished, I think, second to last. And this is what Fred Brooks talks about as kind of the second system problem, where kind of the first time you do something, you're uncertain, you measure everything, you monitor everything, and then you become overconfident and say, I know what this is going to be. And he kind of, they learned the lesson in 2004, they started measuring again, and then 2007, they actually won the whole season. So kind of the key thing here is complexity grows without us intervening. Complexity grows even more when we intervene, but entropy kind of is just going to be entropy anyway. And we need to kind of seek active feedback. We can't stop monitoring. Even if you've monitored something and you say this is perfect and we know what it is, keep monitoring, keep seeking active feedback there. And kind of that's pretty much it. I'm going to finish now, and just to leave you with something more pragmatic than do small components and integrate. We kind of really need to model for the vectors of change. And we need to anticipate these vectors of change. You might not get everything right, but the kind of commonality, variability analysis, stuff like that can help that. Fighting accidental complexity is critical, and figuring out what are we doing just because we can do it? What are we doing because it's an experiment? And what do we want to kind of really do, where the essential complexity is critical. Building a theory about what we're doing and properly building it, not kind of the XP thing where, oh, it's a metaphor, so this is a cow, it's going to behave like a cow. It's not a cow, it's a software system. It doesn't behave like a cow, but building a theory about it, communicating it, logging it, being able to kind of revisit it later is critically important, because then people will know how to change it in the future. And then kind of really knowing when to change stuff and monitoring is really, really important. Given that, the best we can aim for is aiming for resilience, and aiming for resilience is going to reduce the risk of bad decisions, which makes, again, things less irreversible, which reduces kind of all this accidental complexity. Thank you very much for your time. Hopefully I've tickled your imagination a bit.